What's up, everybody? Welcome to this. What is this? The 8th lecture of trig. By now, I'm sure all of y'all are wondering. Okay, so all of this is cool because you're definitely saying that all of this is cool, and wondering when are we going to get to use it? When are we going to do something with it? Like when are we going to apply it? What does this stuff get used for? That's all this lecture is going to be about. A bunch of different examples. To start off with, thought we'd start off with this example up here. So what we've got is a right angle triangle with two sides whose lengths are unknown and one angle unknown. Meanwhile, what we do know is that this angle here is 90 degrees. This angle here is 34.2 degrees. And that this angle right here is 19.4 degrees. Okay. So I claim we're going to use trig to solve this, but how? And what are we solving for? Well, we're going to find all three of these unknowns. We're going to find the length of both sides and the missing angle. Okay, so how are we going to do that? Well, we can start by just looking at the things we do know. What we know is that in a right angle triangle, these two angles are going to add up to 90 degrees. And that's because in every triangle, all of your angles add up to 180. Well, we already know this is 90 degrees, so that must mean these two add up to 90 degrees. Okay. So, alpha plus beta is equal to 90 degrees. We know alpha is 342. Alpha is 34.2 degrees. So we can find beta then. All we have to do is subtract alpha from both sides, and that's going to give us beta, right? Okay, so let's do that. Beta is equal to 90 degrees minus 34.2. Okay, so that's going to be 55 degrees left over, right? 55.8 degrees. So we know beta this angle is 55.8. So what else do we know? Well, we know that a squared plus b squared is equal to c squared. That's one thing we know. We also know that cosine of alpha is going to be equal to A over C. My mistake, I meant to say B over C. Sorry about that, guys. So cosine of alpha is equal to B over C. Sine of alpha is equal to A over C. We also know that tangent of alpha is equal to opposite over adjacent. So A over B. All right, so we have some things we know. And just for good measure, let's go ahead and write out the Pythagorean theorem. A squared plus B squared is equal to C squared. So looking at this, let's now write out the constants that we know up here. Alpha is equal to 34.2. We also know what B is, 19.4. B is 19.4. So in each of these equations, we have our trig function, which takes in alpha, and we know how to calculate that. And we know our B. The things we don't know, though, are C and A. So those must be the things we're solving for, right? So how can we set up these problems to solve for that? Well, we can start by looking at, say, cosine, and saying, all right, well, if I multiply both sides by C, I'm going to have C times cosine of alpha is equal to just B. So if I divide B by cosine of alpha, that means I've got C. So let me write this out. What am I saying? So we know cosine of alpha is equal to B over C, which tells us that C times cosine of alpha is equal to B. Well, I know cosine of alpha and I know B. I'm trying to solve for C. So if I divide now both sides by cosine, we're going to have cosine is equal to B divided by cosine of alpha. And I can start plugging in values now. And I can say, all right, cool. I've got this. So this means C is equal to 19.4 over cosine of 34.2 degrees. Now this is the part of the lecture where you discover I don't know everything. Because I don't know what 34.2, the cosine of that is. I have no idea. I know it's not going to be a good, nice, even number to divide by. So I'm not going to know what it is to divide 19.4 by cosine of 34.2 degrees. So you might be asking yourself, well, Matt, if you don't know, how are we supposed to know? You're not. This is where you pull out your calculator and you type it in. And that's what you should do. Put it in your calculator and find out. Myself, I'm going to pull out my notes because I know it's in my notes. After you put all of this together, you type it in your calculator, what you should come out with is approximately 23.46. Okay, so C is going to be equal to 23.46 approximately. Having said that, a note about notation. The squiggle lines, all that means is I have no clue what comes after these decimals, but I know I chopped off some stuff after the decimal. So I just took it to 2 digits and stopped there. I have no idea what the other decimals are. So this is an approximation. But it's a pretty decent one. Takes it out to the 100th place. That's decent. So, we now know that C is equal to 23.46. Now all that remains is finding A. Now you might be looking at this thinking, oh, I don't want to apply the Pythagorean theorem. Because that's what obviously jumps out at us. We know C, we know we know B. So using that, we can rearrange and solve for A. I don't want to do that either. Matter of fact, I'm not going to do that. I'm going to do something different. I'm going to use the tangent. Because we know what tangent of alpha is, or at least we can put it into our calculator and find out. And we know that whatever that value comes out to be, it's equal to the ratio of A divided by B. And I know what B is. So I can find A. All I've got to do is say A is equal to the tangent of alpha, this quantity, times B. So just multiply both sides by B. So let's do that up here. So we know tangent of alpha is equal to A over B. We know B, we know alpha, we're solving for A. So we want to multiply both sides by B. So we go ahead and start plugging in numbers now. (19.4) times the tangent of 34.2. Degrees. So again, I have no idea what the tangent of this is. I know it's not going to come out to be a nice number. So I'm not going to have any real way of calculating what 19.4 times the tangent of this not nice number will be. So we type it into our calculator again. I am just going to go back to my notes. And looking at it, we get that this is approximately equal to 13.18. These are approximations, so we use squiggles. 13.18. And yes, I just called that symbol a squiggle because I don't know the actual name of it. I've always just called it the approximation symbol, but it's squiggles. It looks like waves. So, having solved these, let's go back and check to see if there's anything left that we don't know. We've got the length of this side. That's 19.4. We've got the approximate length of this side. That's 13.18. We've got the approximate length of the hypotenuse. That's 23.46. We found this angle. That's 34.2 degrees. We found this angle. That's 55.8 degrees. And we know this angle is 90 degrees. So we've got everything. There's nothing else we can solve here. And that's it. That's all I've got for this example. So let's look at another one. All right. So in this next example, what we've got, other than a great work of art, is a problem where we've got this building on fire, right? And the fire department has a ladder that's 110 feet long. The catch is it can only lift up to 72 degrees. So it can only be elevated up 72 degrees. Okay. So we got that, 72, 110. We want to know how high this ladder is going to be able to reach. Well, if we look at this picture, we've got a right angle triangle. We've got a right angle here, 72 degrees here, and we know the length of the hypotenuse. So it looks a hell of a lot like this top triangle. We've got 110 feet for our hypotenuse. Our alpha here is 72 degrees. But we want to know how high that ladder is going to reach. So what we're going to try to solve for is A here, right? Because that would be the corresponding leg. How high up? It's going to be opposite of 72 degrees. Okay. So how are we going to solve this? Well, we're going to call the fire department and ask them what the answer is, because they ought to know. And if they don't pick up, we're going to apply trig. We're going to say, all right, well, I'm trying to find the opposite of the known angle. I'm trying to find the length of the opposite edge. I know the hypotenuse. Well, this is starting to sound a little bit like sine, right? Because sine of alpha is equal to our opposite leg, in this case A, over our hypotenuse, in this case 110 feet. Well, we know alpha here is 72 degrees. So all we've got to do now is multiply both sides by 110, and we can solve for A. So doing that, we've got 110 times the sine of 72 degrees is equal to A. All right, well, because I don't know what that is, I don't know what the sine of 72 is. I know approximately where it's at, but I don't know the actual number. We're going to type it into our calculator. Or look at our solution key. And what it comes out to be 104.6. So A over here is equal to 104.6 feet. And I should have said approximately. And that's it. That's all we set out to solve. We just wanted to know how high up the ladder will reach. This height. That's what we just solved for. That's it. So, before I go any further, I wanted to point something out. We didn't actually have to use 72 degrees. See, because we know this angle has to be 18, because 18 plus 72, that's up to 90. And instead of using this angle, we could have used that angle, in which case we would have had to use the cosine. So it doesn't matter which angle we use, we could have just as easily said, all right, because beta is equal to 18 degrees, because of this, we could say cosine of 18 degrees is equal to A over 110. Now, why is that? Well, the reason why that is because when we're talking about beta, the opposite side is B, and the adjacent side is A. So remember, which side you talk about when you're talking about opposite and adjacent is going to depend on which angle you're using. So with this angle, the 72 degrees angle, A is our opposite side, and B is our adjacent side. With this 18-degree angle, B is our opposite side, and A is our adjacent side. Now notice, in both cases, the hypotenuse stayed the same. That's because the hypotenuse is always the side opposite of our right angle. It's always the opposite side of that corner. Always, always, always. So, solving this the rest of the way out, we could have said, all right, well, because of this, A is equal to 110 times the cosine of 18 degrees. So we could have gone about it in two different ways. We could have also calculated what B was and then used the Pythagorean theorem. So it's not a case of one size fits all. We can go about these problems in a couple different ways. This way was the quickest because we didn't have to find beta, but we could have used the other ways. Cool. So, something else to point out. All through this lecture, I'm going to be referring back to my notes. I'm going to refer back to my notes because trig functions don't usually come out to be nice numbers. The sine of 36 degrees. I don't know what that is. The sine of 72 degrees. I don't know what that is. Sine of 42 degrees. I have no wild idea. Outside of the unit circle, I don't have these memorized. I can approximate them, but I don't have them memorized. It used to be that mathematicians would go and use books like these giant textbooks full of tables. And for anyone who just called me old, you're valid. You just failed. No, I'm just kidding, obviously. But it used to be that we would use these tables. Now, we obviously have calculators that will calculate this for us. And the reason why I'm making this segue is because I want to make a point to y'all. You have resources. Use them. All of them. Use your calculators. There are two websites that I would suggest you look at, Wolfram Alpha and Symbolab. So, take the moment to write these two websites down. Wolfram Alpha and Symbolab. Now I'm telling you about these websites because most of y'all are going to figure out where they are, what they are on your own. And if I let that happen, I have no real say in how you use them. I don't get to give you advice on how to use them and what's responsible use with these. But if I tell you about them, I do. So, I am okay with y'all using these resources on your homework, not on your exams. Do not use Wolfram Alpha or Symbolab on your exams. Under any circumstance, do not use them on your exams. You can, of course, use calculators, because again, I don't know what half of these trig functions come out to be. I don't even know 3/4 of them, or I mean 1/4 of them. I'm trying to go the other direction, right, smaller. And I don't expect y'all to either. Like I said, mathematicians used to use these giant textbooks. And the thing's the size of my face put together. So don't feel like you need to know what the sine of 13 degrees is or the tangent of pi cubed. Like, I don't know. You don't need to either. That's the point of this class, to figure out how to use these things. Now, getting off my soapbox, getting back to the lecture at hand, let's check out some more examples. All right, so what we've got in this example is we're standing 200 feet away from a factory. And we want to know exactly how tall, how high up the top of the smokestack of a factory is. All we know is that looking up, we have to look up 35 degrees to see the base of where the smokestack starts. And then we have to look up 53 degrees to see the top of the smokestack. But what we want to know isn't just how tall the smokestack is. We want to know what S and A are. In particular, we want to know what S is. Because notice, we can use trig on the big triangle to find out how high it is. And we can use trig on the small triangle to figure out how tall the building is without the smokestack. But how do we find out how tall the smokestack is? How do we find out this height? So, looking at it might not be obvious right away. But when we draw it as a triangle, we can kind of start getting an idea of what to do. We know that this side, the length of this side, and the length of this side are going to relate in a very particular way, right? By tangent. So we can use that to start calculating things. In particular, what we can do is we can say, all right, this smaller triangle, this is going to be A, this is going to be 200 feet, and this is going to be 35 degrees. Well, if I want to find A, that's the opposite side from my angle. And I know the adjacent side, so I can use tangent. Okay, let's apply tangent. What we know then is that tangent of 35 degrees is equal to A over 200. All right, so looking at this, we know multiply both sides by 200. 200 times tangent of 35 degrees is equal to A. All right, cool. Now, looking at the next triangle, what we've got is going to be something like this. 200 feet, 53 degrees. All of these are right triangles, right? Because presumably, assuming nobody crazy builds this building, it's going to form a right angle with the ground. So we know all of these triangles are right angle triangles. So now we want to know what the length of this other side is. But notice that 53 degrees, the length of this whole side is going to be A plus S. Okay? So this is A plus S. And based off the other problem, we already know that 200 degrees times the tangent, 200 feet, my mistake, times the tangent of 53 degrees is going to be equal to A plus S. Well, we just solved A, so we can subtract A from both sides. When we do that, we find that 200 feet times the tangent of 53 degrees minus A is equal to S. And after doing all of the math, what we come out with is that length is approximately 125 feet, 125.4 feet. So what we just found is S is approximately 125.4 feet, and A is equal to whatever the 200 times the tangent of 35 degrees comes out to be. I didn't calculate what that comes out to be, so I don't know the actual number. But to review how this problem worked out, what we're saying is we've got these two triangles and they're embedded in one another. We know how to calculate A because we know the angle to the top of A, right? That was 35 degrees. We don't know how to calculate S, but that's what we want. But we do know that standing 200 feet away to look up at the very tip top, we have to look up at an angle of 53 degrees. And the length of this entire side is going to be a plus s. So we can set it up and solve for s. Having said that, let's look at a couple more. So have you ever noticed that if you were to take a spring and pull it down to a certain point, that jump up and down, up and down, up and down, well, that jump could be described using trig? Of course you have, because you're good math students, right? And that's the sort of thing that all normal people would notice. Well, that motion, that up and down, up and down, up and down, is an example of what's called simple harmonic motion. Simple harmonic motion is motion that can be described in the following way. D is equal to A times sine of omega t, or D is equal to A times cosine omega t. Any sort of motion that can be described with either one of these equations is called a simple harmonic motion. So in the example of a spring, we can pull it all the way down, let it go, and it's going to bounce up and back down, up and back down, up and back down, just like sine or cosine. In the case of cosine, it goes down, then back up. In the case of sine, it of course goes up, back down. Having said that, there's some details we need to know about this. First, what is this d? This d is really just the displacement. It's the distance it's traveled relative to some equilibrium point. So in this example, pulling a spring down, we pull it down to a distance of negative a. It passes through some equilibrium 0 point, and it compresses back up to an a, to a height of a. And it keeps doing that on and on and on. That d value would be where it sits along this line. The a value is going to be the amplitude. So what about omega t? Well, omega t is a little bit harder to describe. What omega t tells you is how fast it's moving. So t being time and omega being the speed at which it oscillates. Having said that, two details we need to really quickly talk about is the period of one of these things is going to be 2 pi omega. And the frequency is going to be omega over 2 pi. You can see why I had to look at my notes. It's easy to mix those two up. So, having said this, you're probably wondering, well, this doesn't seem like an exact example. Do you have a better one? Yeah, I do. We're about to look at one. All right, so in this example, what we've got is a spring that has been bouncing up and down. And we want to create a model having measured it from the equilibrium point. Now what we know about this spring is that the maximum displacement it ever experiences from the equilibrium point is 10 and negative 10. And we know that the period heard is 4 seconds. Now I said we want our model to work starting at the equilibrium point. That means in our choice between sine or cosine, we're going to want to use sine, right? Because sine at 0 is 0. So let's write that down. We know we're going to start using sine at 0. And it's going to be omega times t. And we just said the amplitude is 10, right? That's the maximum displacement it ever experiences. So, 10. So it looks like we've got our equation by and large, right? We're just missing one term, one value. What is this omega term? How are we going to find it? Well, the problem tells us that the period is 4 seconds. We know that this means then 4 is equal to 2 pi over omega. We can multiply both sides by omega and divide 4 from both sides. So it's going to look something like this. Omega times 4 is equal to 2 pi, which is then going to tell us omega is equal to 2 pi over 4, or just pi over 2. So we just found omega. Omega is pi over 2. And that's it. That's our equation. That's all we got. The only thing that could possibly change is if we knew that from being measured at 0, if it was going in a negative direction first, we would change this to negative 10. But because we don't know which direction it's moving in, we can assume positive. It doesn't matter. It's a matter of perspective, how you want to measure things. So all we've done here is we've said, I want to create a model for the motion of this oscillation. I want my model to start at 0 when time is 0. And I know that the period of this motion is going to be 4 seconds. So that lets us find omega. And we also know that the amplitude is 10. So putting all of these things together, we've got the amplitude, we've got omega, and we know because we're starting at 0, we're going to use sine. If on the other hand we were starting at the top or bottom, we would use cosine. Having said that, this particular problem is actually in your notes. If you go to section 1.8 towards the very end of the slides of either the PDFs or the PowerPoints, you should be able to find this problem. Like I said, that's section 1.8. Having said that, we got one last thing for y'all. So for this last little bit that I've got for y'all, it's just really a definition and explanation for what these things are. bearings. When people talk about bearings, what they're really just saying is a measure of where you're looking or where you need to go relative to north or south. So, for example, if I were to say south 35 degrees east, what I'm saying is measuring from south, we want to find the acute angle in the eastward direction. So the acute angle is going to be that angle right there. It's in the eastward direction. That's south 35 degrees east. North 30 degrees west is going to be measured from north. So we're moving 30 degrees from north in the direction of west. And that's going to be right about here. So really that's all that I've got for bearings. You say from which direction, north or south, what degree, and in the direction of east or west. That's pretty much all there is to it. Having said that, I'll let y'all go. Have a good one.